Hey guys, today we are looking at 4.6, Fundamental Theorem of Algebra, and then we'll also be looking at Descartes' Rule of Signs. So I'm not going to read through every single one of these theorems and rules that we have here. I'm going to go ahead and summarize all three of these and combine them together to tell us what's important. Basically what these three rules are: the Fundamental Theorem of Algebra, the Linear Factor Theorem, and the number of zeros of a polynomial theorem, basically tells us that whatever our degree is of our polynomial, we have to have that many zeros between our real zeros, our multiplicity, and our complex or imaginary irrational rules. So our total degree has to match up with how many solutions we have, how many roots we have to our problem. Again, combining together, including multiplicity and complex or irrational solutions. They have to match. So let's go ahead and just recap real quick a problem that we looked at back in 4.5 and just make sure that this matches up and is legit. So if we're asked to find all the zeros of the polynomial, we're going to ignore that second part. I'm not super concerned with writing them as a product of linear factors. Let's just find the zero. Let's just find the zeros, find all the solutions. So in this we have x to the fourth minus 6x cubed plus 10x squared plus 2x minus 15. So definitely not factorable using our traditional methods. Right? There's 5 different terms, so we can't do it that way. We're going to have to go to that rational root theorem, where we're looking at factors of 15 over factors of 1 to be able to come up with a list of ones to go off of, and then we can kind of start checking things from there. So in this case, we have our list of possible rational roots. Since my leading coefficient is just 1, it really is just my factors of 15. So I've got plus or minus 1, plus or minus 3, plus or minus 5, and then plus or minus 15. Right, those are my only 4 they're my only 4 factors of 15. 1 times 15 or 3 times 5. So that's our list. So I'm going to go ahead and just start picking ones. Now I'm going to save us some time and cheat a little bit, so we don't have to keep guessing and checking. Let's just say, oh, hey, let's pretend we just guessed positive 3 first. So here, I'm using synthetic division. Sorry, spaced for a second. Synthetic division to check and see if something is a solution. Basically, again, we're checking to see if it has a remainder of 0. So 1, negative 6, 10, 2, and negative 15 are my coefficients. So if I do synthetic division rule on this, drop this down, multiply, add them up, multiply, add them up, multiply, add them up, multiply, add them up. Hey, look at that. We get a remainder of 0. Cool. So positive 3 is one of my roots. So actually, in this case, since we're just looking for the zeros, this positive 3 is my first one. Now from here, we could try and rewrite this and factor it out. This would be 1x cubed minus 3x squared plus x plus 5. But looking at that, it's even something I'm still not comfortable with being able to say that we could even factor that using factor by grouping, because it's still a 4-term thing. So what I'm going to do is take this polynomial that I started with and do synthetic over again. And I'm going to do 1, negative 3, 1, and 5. And I'm going to go ahead and check it with some factor. Now, we already checked positive 3, so that's going to be kind of off my list. And now looking at this, my constant of this new polynomial is 5, which means I've eliminated 15 from my list as well. So positive and negative 5 is still an option, and actually negative 3 is not an option either, because that's not a factor of 5. So it could be negative 1, it could be positive 1, could be negative 5, could be positive 5. I'm going to just, again, totally randomly check negative 1. Maybe negative 1 will work in this situation. Positive 1 here, multiply to get negative 1, adds up to negative 4, which adds up to positive 4, or multiplies to positive 4, adds up to 5, negative 5, and 0. Hey, look, 0. We're happy with 0. So far, 3 and negative 1 are 2 roots that we know of. Now this one is just a quadratic, so I'm pretty confident we could be able to handle this one that's left, because so far we've got basically, if we wanted to write it out as factors, x minus 3, x plus 1, and then this thing that we're left with is x squared minus 4x plus 5 so far, factored out. And since I'm trying to find all of the roots, right, this already we know is x, let's write it in a different color. Let's do this in green. This we know is x equals 3. This we know is x equals -1. Those are 2 roots so far. This next one looks like it should be factorable, right? Positive, something that multiplies to get +5 but adds up to -4. But that doesn't because of my signs. If my signs are flip-flopped, I could do this, but to get +5, I either have to multiply -1 times -5 or +1 times +5, which does not work. Which means, unfortunately, we have to pull out our favorite friend from the past time, x equals -b plus or minus the square root b squared minus 4ac all over 2a. Yeah, quadratic formula coming back from the dead. So, in this quadratic that we're trying to solve, we have a value of 1, a b value of -4, and a c value of 5 to solve this bad boy, since it's not factorable. So I'm going to go ahead and just plug that stuff in. I'll just keep it in red. So x equals -4, so +4, plus or minus. I'm just going to kind of skip some steps here because you guys are smart cookies. B squared, which -4 squared is a +16, minus, we've got 4 times a, so 4 times 1 is 4, times c is 5, 4 times 5 is 20, all over 2 times a, which is just 2 times 1, so just 2. So as we continue simplifying here, that's 4 plus or minus the square root of -4 all over 2. So this is going to be an imaginary solution because we know that the square root of -4 is 2i all over 2. So here we can simplify this one of 2 ways. Both of the top numbers are divisible by my denominator, so I could just simplify and just say that this is 2 plus or minus I. And those are my last 2 roots, which makes sense looking at my original degree. I had degree 4. I had 2 solutions that were real numbers, and then 2 solutions that are imaginary, are plus or minus 2i. 2 plus or minus I. 2 plus I is our first one, 2 minus I is our second one, 3 is our third, -1 is our fourth. All right, so getting into the second half of this lesson is Descartes' rule of signs. Now, we've been able to, so far with those first 3 theorems, figure out and kind of know how many solutions we should be looking for, which helps us a little bit. But Descartes' rule of sign actually narrows it down even further, where we'll be able to figure out how many positive solutions we have and how many negative solutions we have. So what we have to do here is a couple of different things. We've got we've got to attack this in 2 different stages. So what Descartes' rule of sign, and this Descartes is a very, very smart old dead dude who did a lot of just thinking for his career. He realized that in a function, the number of times the function changes from positive to negative tells us our possibilities for how many positive solutions we would have. So, or that number increased or decreased by an even number. And that's, again, that's important. That's what I'm just basically summarizing here from this first rule. The number of positive real zeros is equivalent to the number of variations in the sign, or again, going up or down by an even number of, going down by an even number of that number of variations. And that is because of our complex numbers always coming in pairs. So for example, we'll see one where like maybe we have 3 different variations, 3 times my sign changes from positive to negative. So we could have all 3 of those be real positive numbers, or we could have a pair of those kind of split off and we're going to make those imaginary, in which case we'd only have 1 positive real solution. So what we have to do for these we kind of start with our lead coefficient. So I'm going to zoom in here. We're going to start with our lead coefficient and just try and figure out how many times my sign changes. So I start off with my first term at positive. Here is one sign change to negative, two sign changes to positive, and then I don't change signs again until my -6. So this has a total number of variations of 3. 3 is my maximum number of positive real zeros here. So I could, again, have 3 of them, or I could decrease it by an even number, so by 2 in this case, because I could have a pair of those real solutions split off, and now those are going to be complex numbers. That's another possibility for us. Okay. For our negative real zeros, it's a little bit different, because we don't just take my original function as it was written. So I'm looking at this sentence here in blue. What we have to do is plug in a negative x into our function. Again, where he came up with this, I have no clue. He was obviously a very, very bored guy who just sat around and thought about numbers a whole lot, which he is. He's one of the most famous mathematicians in all of history. That's why our coordinate plane is called the Cartesian plane. Descartes, named after him because he's that good. The Cartesian plane. Anyway, so what we have to do here is plug in a negative x into our equation. So what you could do, you could go through and actually plug them all in, where you say, all right, well, let's just go ahead and do this. Negative x to the 4th power minus 5 negative x, messing this up already, negative x cubed plus 5 times negative x squared plus 5 times negative x minus 6. And then we have to go through and evaluate. A negative x to the 4th power is still a positive x to the 4th. This negative x cubed, or negative x to the 3rd power, is still a negative x after we evaluate, but we have that negative out in front, so that's going to become a positive 5x cubed. Negative x squared is a positive x squared, right? Negative times a negative is a positive, so this stays as positive 5x squared. This is now negative 5x, and that is negative 6. So now when we do that analysis, we start out positive, we only switch once, right? Because my x to the 4th is positive, x cubed is positive, x squared is positive. It's not until you hit that negative 5x that you finally hit a negative number. So I've only got one switch, so I only have one possible negative 0, which actually we want that to be the case, because that tells us there's no other option. We have to have one negative real 0. There's nothing else. I have to have exactly one. I can't have none of them. I can't have 3 of them. I can have one exact one. So that could narrow our list down, and we could say, all right, well, let's look for the negative first. We know there's at least a negative. Let's try and figure that out first, and then we'll move on and say, all right, well, once we found that, all the rest of our solutions have to be positive. So this next little section here, this is our kind of analysis. This is our way of being able to break this down a little bit further. So what we have here, and I'm going to kind of extend this, make a nice little table here. We had 2 different possibilities for positive real solutions. We said our number of variations was 3, or it was 1. We had exactly one possibility for my negative real zeros. 1 was it. What I know is that my original polynomial had a degree of 4. So I know, based on those first 3 formulas we looked at, those first 3 theorems, was that I have to have 4 total degrees. I have to have 4 total roots. Well, this top one, I have 3 positives and 1 negative, which means that's 4 already. So that means I would not have any imaginary solutions if that is the case. But I do have this other option where if it is exactly 1 positive real solution, it's exactly 1 negative real solution, then I would have to have 2 of my solutions be imaginary. And that is a possibility for us as well. But these are the 2 options for this function. I could have 3 positive real solutions, 1 negative real solution, and that's it. Or I could have a real solution that's positive, a real solution that's negative, and then two imaginaries. But that's basically what we're doing here. We're trying to, again, take our list of all these possible rational roots and narrow it down even further. We want to try and minimize how much guessing and checking we have to do in a polynomial in order for us to be able to figure out our answer. So let's go ahead and try this again with b. With b, I am starting off with an x to the 5th power, and from my original, I go from positive to positive to positive to positive to positive, so I don't have any variation in my problem at all. I have 0 variations, so I have no positive real numbers, which is awesome for us because that takes our list, chops it in half. We don't have any positive real solutions. We can just focus on the negatives, and then whatever doesn't work out from there has to be imaginary. As a little shortcut, if you guys didn't recognize when I went through, and I know I kind of did this the old-fashioned way the first time, when you plug in that negative x value into your equation, anytime you have an even exponent, we know that that's always going to make it positive. And anytime we have an odd exponent, when you raise it to that odd power, a negative would stay negative. So basically what we can do here as a shortcut is anytime you have a term that has an odd exponent, it's going to switch signs, either from positive to negative or negative back to positive. And anytime you have an even exponent, it's going to stay the same sign. So that coefficient is going to stay the same. So without having to actually plug anything in for part B here, I know that when I evaluate p of negative x, my first term is going to change because it's got an odd exponent. So now it's negative 2x to the 5th. This is going to be a minus 3x cubed. That's still going to stay the same here, positive 5x squared, because it was an even exponent and staying the same. This 8x is going to become negative because it has an odd exponent. And then that positive 7 is going to stay just positive 7. There's no x to adjust. So now for my negative zeros, I start off negative, I switch once to positive, twice to negative, 3 times back to a positive. I have 3 variations. I have 3 times my sign changes. So that tells me for this part, since I have 3 variations, I could have all 3 of them be be negative zeros, or again, I could decrease by that even number and replace that with a positive 1. So that's always going to be the case. So now looking at my possibilities, and I'm just going to go ahead and extend my table. I know I'm not going to have any zeros for my positives. Not an option. But I have the 2 different options for negative real numbers. I could have 3 of them, or I could have just 1. Since I know in this case that since my original degree was 5, I should have 5 roots between multiplicity and imaginaries in real solutions. So option 1 could be all 3 negatives are there, which means I have to have 2 imaginary. If it is the case where I have only 1 negative 0, then I would have to have 4 imaginaries to get to that total that I need. So again, this process just helps us narrow down the way that we can find those roots when it's not something that's factorable. So on this next part here, again, I'm not going to linger on this for a long time. You guys have this available to you. You can pause the video now if you want to read all the way through this. What we're going to be doing is combining all of this information that we have to narrow our list down together. And then we're going to use that to solve. So rather than just like throwing darts out into nothingness and hoping that we hit a solution that actually works in my problem, we're going to start by narrowing down that list. So we're going to look at our degree. We're going to figure out how many zeros we should have. We're going to use that rule of sign to be able to determine how many of each sign we should have and how many are going to be imaginary or not. And then we're going to start with what we did for part 2 of 4.5. Start with that list of rational roots, and then we can kind of narrow down from there to be able to figure it out. So let's go ahead and do that here with exercise 3. So we're asked to find the zeros of x cubed minus 7x squared plus 16x minus 12. So first things first, we are going to have 3 zeros between multiplicity and those imaginaries, and obviously our real roots. So in this one, our rational roots, our possible rational roots would be factors of 12 over factors of 1, so really just factors of 12. So we've got plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, plus or minus 6, and plus or minus 12. So 1, 2, 3, 4, 5, 6. We've got 12 different possibilities for possible roots. Now, for our Descartes rule of sign, we need to look at how many variations we have in our original. That's going to be our positives. I'm going to go ahead and just write this down. Positive roots, and then our negatives. We're going to have to do that sign flip. So, again, looking back up here to my original equation, I start off positive, I go negative, positive, negative. So I've got 3 variations. So I could have 3 positive solutions or just 1. Again, it's always whatever that number of variations is, minus factors of 2, right? Minus even numbers. For my negative numbers, remember I have to do that sign change. So I'm going to go ahead and do that in blue here underneath. Again, any of my odd exponents have the sign flip. All of my even exponents have the sign stay the same. So this x cubed becomes a negative x cubed. My x squared stays the same, so still minus 7x squared. My x to the first power, since that's odd, is going to switch signs, so now that's negative 16x. And then my negative 12 stays the same. So the nice thing is here, all of these are negative, so there's no variation. So we just figured out from that rule of signs that there are no negative zeros, which is super helpful for us because that eliminates all of these possibilities. It can't be any of our negatives. It has to just be our positives. So now our list has gone from 12 down to 6, which is awesome. Super awesome. So the way that I write this up, I know I showed you guys kind of the table all typed up nicely, but the way that I usually do this kind of on the fly in my Scratch work, I've got positives, I've got negatives, I've got imaginaries, and then I've got the total. So I just make a nice kind of little table like this when I'm doing this on the fly. So my options here, if I have 3 positive zeros, I know I'm not going to have any negatives. My original degree was what, 3? So if that's the case, I don't have any imaginary. All 3 of them are positive. That's option 1. Another possibility, if we have exactly 1 positive real solution, again, we know there's not any negatives, so that's not an option. That tells us that I have to have 2 imaginaries in order to get to our total of 3. It always has to be 3. Between multiplicity and the imaginaries, along with obviously our real numbers, that has to add up to our highest degree. So from here, now I can go ahead and start testing out some things. But again, I've got this list narrowed down to just positive numbers, and I know here that I've got these different possibilities. So I'm going to go ahead and just start guessing and checking at some. Well, that was fun. What you guys just saw was the power in Hebron going out while I was recording the video. You could notice, if you go back probably about 5 or 10 seconds, you can hear the sigh of frustration. I'm very proud of myself for not swearing so I could post that video. So that's fun. Let's pick up where we left off in this problem. So we know in this one, we have that there are 2 different possibilities. Right? Either all 3 solutions can be positive, 1 solution can be positive, but we know there's not going to be any negatives. So we've narrowed that list down quite a bit. We have positive 1, 2, 3, 4, 6, and 12. Those are our possible rational roots. So we're just going to start guessing and checking. We're going to start plugging some stuff in to see if it works. I usually like to start towards the middle of the list. So let's go ahead and just try 4, see if that one works. So if I try 4 in there and do synthetic division, my original problem here was 1x cubed, negative 7x squared, 16x, and then negative 12 minus 12. So if I go through and do synthetic on this, that's a 1 times 4 is 4, which adds up to negative 3, negative 12, 4, 16, and that's 4. So 4 is not one of our solutions, unfortunately. So we can just kind of work our way down the list, or you can jump around, whatever makes you happy. You know, it's up to you. Let's just try, I don't know, let's try 2, 3, 3. 3 sounds good. We'll work our way smaller on the list. So 1, negative 7, 16, negative 12. So, again, as I go through the synthetic process, I just drop this first one down, multiply, add up, multiply, add up, multiply, add up. Hey, yo, we found our first one. So, positive 3 is one of our roots. So, x minus 3 would be that solution. X minus 3 would be that factor. What I'm left with now is x squared minus 4x plus 4, and that was times my x minus 3. So I have to factor that right parenthesis, what I was left over with, further. That does factor out perfectly into x minus 2 times x minus 2. So we've got positive 2 as a solution twice. And here, since they asked us to find the zeros, we would say, I'm going to do this in green, x equals 3 and 2, and here we'll just put the little note here, this 2 has multiplicity of 2. So even though there are only two unique solutions, right, only 2 unique roots, because that 2 has multiplicity of 2, that does still count towards our total of 3 that are required in order for us to have the right number of roots, because our degree originally was 3, so we had to have a total of 3. All right, one more and then we are done. So for this last one, again, instructions are the same. Find the zeros of 3x to the 4th plus 23x cubed plus 56x squared plus 52x plus 16. So to start off with, let's start with, we know there's going to be 4 total degrees, so let's just start with Descartes' rule of signs. So looking at this originally, so we're trying to figure out how many positive, how many negative there are. So in the original one, there's no sign changes, right? Positive to positive to positive to positive to positive. So there are 0 possible positive roots. That's good. Narrows our list down again for us. But we have to look now at our negatives. So again, for these, we're only looking at, if we plug in a negative x in for our x value, looking at those odd degrees would switch signs, those even degrees would stay the same. So this now becomes, this x cubed, or x to the 4th stays as it is, so this is still positive. Oops. So here, I'm just noting above what their signs are. This x cubed becomes negative, our x squared stays positive, our x to the 1st goes negative, and this constant stays positive. So in this case, we have positive to negative 1, 2, 3, 4 sign changes, 4 variations, which means we actually have a lot of options, because again, they come in pairs for our complex numbers. So I could have all 4 negative numbers, negative solutions. I could have 2 negative solutions, or I could go all the way down to no negative real solutions. I've got all 3 of those that are possible. So when I go to that table that we were working on before, we've got our positives, our negatives, our imaginary, and the total. We're going to have more. We're going to have more rows, because we have one of our options has 3 total possibilities. So for our negatives, we could have all 4, we could have just 2, or we could have 0. For our positives, we know there's not going to be any of them, so those are zeros all the way down. We know that our original degree was 4, so our total has to be 4. So then obviously you can see here we would have no imaginaries in the first case, 2 imaginaries in the second case, and then all 4 of the solutions being imaginary in the third case. I haven't shown you any, but we'll do one of those either in class today or tomorrow, depending on when you're watching, or Monday, Tuesday, sorry, when you guys are watching this, where you could have possibilities, like multiple different possibilities for both positive and negatives, and I'll kind of show you how that table looks when we get there. But at least now we have all of our different possibilities laid out here. So next thing would be to figure out our list of possible rational roots. So for this one, we've got, what color do I want to use? Let's use red. So we've got factors of 16 over factors of 3. So for our possible rational, I don't like that. Possible, we'll write all that out. Possible instead of positive. Rational roots. Now, I could ignore all the positive options because I already know there aren't any positive real roots, so I can just look at these as being all negative. So our factors of 16 are negative. So again, just looking at the negatives. Negative 1 times negative 16. We have negative 2 times negative 8. And we've got just negative 4 times negative 4. Is that it? I thought there was more. Well, we'll scooch you on over there. Nice. Another comma here. But we also do have an actual number, not just a 1, for my constant, or sorry, for my leading coefficient. I've got a 3 there. So those numbers that are factors of 16, we can just imagine that those are all over 1. So we actually do have the same thing, but with over 3. Because we could have 1/3, 2/3, negative 4/3, negative 8/3, and negative 16/3. All of those are options for us as well for this problem. So from here, we can go ahead and start taking some guesses. In this situation, I would definitely not start with the fractions. That's going to be my last resort. I'm going to try some regular whole numbers over there first, just to see where we get. Again, I usually like starting towards the middle, so let's just start with negative 4, I suppose. So negative 4 being that factor. Our original coefficients were 3, 23, 56, 52, and 16. All the way across. So from here, and we're going to drop it down. That's a 3. 3 times, negative 4 times 3 is a negative 12, which adds up to 11. Negative 4 times 11 is negative 44, so that adds up to 12. Right? 6 and 6, yep, there we go, which is negative 48 when you multiply, which is 4, negative 16, and 0. Hey, first guess. Awesome. Negative 4 is one of our roots. So again, I'm going to go ahead and shift down 1 row. So I'm just going to look at this new polynomial, 3x cubed, 11 plus 11x squared, plus 12x plus 4. You could, if you wanted to, try and factor that using factor by grouping. But just looking at it, it doesn't look like it's going to be factorable. So I'll do this one more time. So we're going to check it with something else. But we're going to use 3, 11, 12, and 4. Now I know that it has to be a factor of 4. So that means my factors of 4 are no longer, like 8 and 16, sorry, negative 8 and negative 16 are kind of off the books because they're not factors of 4 anymore. So I'm going to try this with either negative 2 or negative 1. So let's just try negative 2 and see if that works. And see kind of where we end up. So that's 3, which is negative 6, which is 5, negative 10, and let's see, 2, which is negative 4, which is a 0. Hey, yo, cool. So far, let's just write out what we got. Because now that we're down to a quadratic, we're down to just an x squared, 3x squared, 5x, and 2. We can probably do this the rest of the way the old-fashioned way. So this is x plus 4 times x plus 2 times 3x squared plus 5x plus 2. So from here, unfortunately, that last parenthesis there isn't factorable using regular old school factoring. If you wanted to, you could go, try synthetic again with maybe like -1. That might work for you instead of doing Xbox factoring. I'm just going to do Xbox factoring real quick because I know that's pretty easy for me, and if nothing else, it's a good refresher for yourself. So if we were going to do Xbox factoring on just this part here, again, I'm going to go ahead and make my box. My first term and my last terms always go there and there. I got to do my x to be able to figure this out. 3x squared times 2 is a 6x squared. My middle term goes down below. So I'm trying to figure out what two things multiply together to give me 6x squared, but add up to a 5x, which of course is a 2x and a 3x. So I'm going to put a 2x here. I'm going to put a 3x here. Doesn't really matter, but that's where I'm putting them. So then looking at my GCFs to factor out my box, 3x in common here, which means this has to be an x, which means this has to be a 2, and this has to be a 1. So all the way factored out, we have x plus 4, x plus 2, x plus 1, and 3x plus 2. So I've got those 4 factors. If you wanted to write out the zeros, which we do need to, this would be -4, -2, -1, and then that one, I'm not going to show the work just because we're already way over time. This ends up being -2/3. I'm just setting each of those equal to 0 to get those solutions. Those are my roots. So in this case, I actually ended up having all 4 of them be negative real roots. Alrighty, lots of information again today. Homework, come on, scroll on over. Homework is up there on the screen on the top, page 202, 4 through 40, every other even. As always, if you have any questions, concerns, thoughts, ideas, hopes, or dreams, make sure you guys are reaching out and letting me know. And I will talk to you guys soon. See you later.